Okay, let's try a little thought experiment. Imagine you wanted to build a perfect digital copy of the world, a simulation, starting from the absolute ground up, from the tiniest particles imaginable. It sounds like something straight out of science fiction, right? Well, today we're going to look at what it would actually take to pull that off.
So, our quest is going to be deceptively simple. We're not trying to simulate a galaxy, not even a person. We're going to aim way smaller. Just 1 cubic centimeter of a simple amethyst crystal. About the size of a sugar cube. And the goal? Build it from the ground up, tracking every single fundamental particle and how they all talk to each other. How hard could that possibly be?
Well, right off the bat, we hit our first hurdle, and it is a big one, the sheer scale. That tiny little cube contains around 700,000 trillion atoms. That's a 7 with 23 zeros after it. Just let that sink in. And that's just counting the atoms. We haven't even gotten to what they're made of yet.
Okay, so to tackle a problem of this magnitude, we're obviously going to need some serious firepower. So let's bring in the big guns. I'm talking about the most powerful computational tools humanity has ever built, the world's top supercomputers. Meet the champions. These are some of the fastest supercomputers on the planet. Take Frontier, for instance. It can perform over a quintillion, that's a billion calculations every single second. We call that an exaflop. These machines have mind-boggling amounts of memory, measured in petabytes. That's thousands of your laptop's hard drives, and they're all linked together with incredibly fast connections. These are the absolute best tools for our quest.
And it's not just those general-purpose supercomputers. We also have specialized hardware, things like NVIDIA's DGX systems or the Cerebras wafer-scale engine, which is basically one single gigantic computer chip. You can think of them as the Formula One cars of computing, built for very specific, very demanding jobs. So with all this power, simulating our little crystal should be a piece of cake, right?
Well, this is where our heroic story takes a very dramatic turn. We've gathered the most powerful tools ever made, we've pointed them at our simple 1 centimeter crystal, and what we're about to discover is that they're going to fail. And not just fail by a little bit, they're going to fail by an amount that literally breaks the laws of physics.
See, the problem is that atoms aren't the end of the story. For a true simulation, a perfect one, we have to go deeper, down to the quarks and gluons that make up the protons and neutrons. And when you do that math, you get about 126 quadrillion trillion quarks in our tiny cube. The scale of our problem just exploded again.
And believe it or not, it gets worse, a lot worse. To simulate the quantum fields where all these quarks live, we'd need to create a kind of computational grid. Just to map out the space inside our 1 centimeter cube, the number of points on that grid would be a 1 followed by 39 zeros. The memory required just to store the starting position is already beyond astronomical.
And now for the real gut punch. Just look at this comparison. To calculate one single step forward in time for our simulation, we'd need about 10 to the power of 42 operations. Now look at the right. The world's fastest supercomputer, Frontier, gives us about 10 to the power of 18 operations per second. We would need 100 trillion Frontiers all working together just to compute a single instant. It's not just hard, it is physically impossible.
And this is a really crucial point. This isn't a problem we can solve by just waiting for better computers. We're running smack into the fundamental limits of physics itself. There's a theory, for instance, that suggests there's a hard cap on how much information can even exist in a certain amount of space, and our simulation would need way more than that. So it's not just hard, it's impossible in principle.
So, is that it? Is it hopeless? Do scientists just throw up their hands and give up? Not at all. This is where the story pivots from brute force to brain power. If you can't solve the problem you've been given, the secret is to change the question. Instead of asking, how can we perfectly recreate reality, scientists ask a much smarter one.
This slide shows the difference perfectly. On the left, you have the brute force way, trying to simulate every single quark. Result? Impossible. On the right, you have the smart way. Instead of perfection, the goal is to predict a specific property, like how strong is this crystal for a new jet engine, or how will this drug molecule stick to a virus. You don't need to track every quark for that. You just need clever approximations to get a useful answer.
So what does this new toolkit of smarter methods actually look like? Well, it's not about bigger computers anymore. It's about smarter algorithms and new ways of thinking that let scientists get real answers from incredibly complex systems, without simulating every single little detail.
So the cornerstone of this smart approach is something called multiscale modeling. The idea behind it is brilliant because it's so efficient. Don't waste your precious computing power on parts of the problem that don't need that much detail. You zoom way in where it matters, and you zoom way out everywhere else.
And here's how it works in practice. For the most critical spot, say where a chemical bond is breaking, scientists use super precise and super expensive quantum mechanics. Then, for the atoms around that spot, they switch to a faster, classical model. And finally, for the vast bulk of the crystal, they use an even simpler model. By stitching these different scales together, they get an answer that is both accurate and achievable. It's the best of all worlds.
And multiscale modeling is just one tool in the box. Scientists also train AI models to basically predict quantum outcomes at classical speeds. They use clever math to dramatically reduce the complexity of their calculations. They even use statistical methods to make really smart guesses instead of calculating every single possibility. Each one of these is like a massive computational shortcut.
So what's the payoff for all this cleverness? Well, this chart says it all. By combining these smart techniques, scientists can slash the computational cost by factors of thousands or even millions. A problem that was once fundamentally impossible becomes something you can actually run on a regular computer cluster. The difference is just staggering.
And this brings us to the practical path to success. By letting go of that impossible dream of perfect recreation, we actually gain something way more valuable: the ability to get real, actionable insights about how the world actually works.
So while we can't simulate 10 to the 23rd atoms, what can we do? Well, using these smart algorithms, we can simulate systems of 10,000 atoms, or even more, with near quantum level accuracy. And it turns out, for most scientific questions you'd want to ask about a material, that is more than enough to get the answers you need.
And this, right here, is the key takeaway of this whole journey. The real holy grail of computational science isn't just about building bigger and bigger machines to throw at problems. The real genius is in developing the ideas and the algorithms that let us sidestep the impossible and find an elegant path to the answer.
Which leaves us with a final thought, doesn't it? This lesson, that asking the right question is often way more powerful than having the biggest tool, applies to so much more than just material science. So what other challenges that we think of as impossible right now are just waiting for us to find a smarter way to ask the question? Thanks for watching.